start chapter 10. And chapter 10 is on liquids, solids, and phase changes. And most of the time is actually going to be spent on liquids, a little bit on solids, and even less on phase changes. So chapter 10, liquids mostly, solids, and then phase changes. So liquids, solids, and phase changes. So if we remember in chapter 8 where we had gases, and I alluded to this chapter in that chapter, remember gases, I don't have connections between particles, right? Each individual gas particle acts independently of our neighboring particles. So gases, we don't have connections between the particles. And we said that's what really differentiated it between solids and liquids, where solids and liquids, we have those connections. And almost all of the behavior of a liquid and a solid are based on the identity or the type of those connections. So liquids and solids, right, these do have connections between the particles. Right, back in 130 or high school, you would have learned that liquids and solids have a definite volume where gases don't. Right, gases can spread out or be compressed because they don't have those connections. Liquids and solids, the volume doesn't vary based on the container because I do have those connections. You can remember volume is the amount of space it takes up, so I can't spread it out, right, because they're connected. I can't squish it together because they're connected. So gases and liquids, we do have connections between the particles, where in gases we don't. So we actually have an entirely different chapter for liquids and solids than we do gases. So the bulk of this chapter is actually talking about intermolecular forces. So intermolecular forces, inter means between, molecular molecules, so these are the connections between molecules, right? Not within a molecule, but between molecules. If I had one water molecule and another water molecule, what's the connections between one water and another water? Right, within water, right, between oxygen and hydrogen in an H2O molecule, I have covalent bonds. But when we say intermolecular, right, we're talking about what kind of connections do I have between molecules. And this is going to be primarily for liquids. Some solids have intermolecular forces too, but they could have other connections depending on what type of solid it is, and we'll talk about that more in another video. So intermolecular forces, these are going to be the connections between particles in a liquid. And then we can put in parentheses, and in some solids. But that's going to depend on what type of solid we have. We're going to have different types of solids. So, and in some solids, but not all of them. So again, if I have liquid water, what's holding one water molecule to another water molecule? And the type of intermolecular forces that it has depends on the polarity of our molecule. So if you need to go back to be able to do this, you're going to need to review Lewis structures, right? Because we don't know how things are connected if we can't draw our Lewis structure or electron dot structure. Once you do that, you need to draw its molecular geometry, right? Because if we drew water as linear, we would say it's nonpolar, but it's not linear, right? It's bent. Because of that shape, it actually makes it polar. Because of that shape, right, because it's polar, it has different intermolecular forces than something that's nonpolar. So review Lewis structure, review Vesper theory. Right, that was our molecular geometry, our shape. And then we needed to assign bond dipoles, and then molecular polarity. essentially what we're going to do is I'm going to list and go through the different types of intermolecular forces, and one of them I'm going to say it only occurs between polar molecules. If you don't know your molecule's polar, then you don't know if it has that type of intermolecular force. So please go and review those if you need to, if they're not fresh in your mind anymore. So types of intermolecular forces. And IMF is our abbreviation for intermolecular force. We can put that up here. So types of intermolecular forces. And the first one I'm going to talk about are dipole-dipole forces. And dipole-dipole forces exist between polar molecules. This is the one I was just alluding to. So these exist between polar molecules. If your molecule is non-polar, it's not going to have dipole-dipole forces. So these exist only between polar molecules. And what happens is the partial positive end of one molecule is attracted to the partial negative end of a neighboring molecule. And then vice versa, of course, right? The partial negative end of one is attracted to the partial positive end of the other. If they're not polar, you're not going to have partial positive and partial negative ends of the molecules. So dipole-dipole forces exist between polar molecules. Has to be polar to have these. So an example for us, water. Right, water is bent. Again, if we drew water as linear, it would be non-polar, so you do have to go back. You do have to know the shape, so if you need to go back and review that, please do. So hydrogen is less electronegative than oxygen. So hydrogens have the partial positive charge. Oxygen gets our partial negatives. I just wrote that backwards. So what happens, and we'll use a red dotted line to represent our intermolecular forces, this partial positive hydrogen is attracted to that partial negative oxygen. And we could draw, more than one in here. I can go draw another one. Again, oxygen is my partial negative, hydrogens are partial positive. If you need to go back and review that, please do it. And that red line is representing my dipole-dipole force. So between one water and another water, dipole-dipole forces are an example of one type of that connection. The second one are going to be hydrogen bonds. And hydrogen bonds are very, very specific. So just kind of bear with me as I write the definition, and then I'll go back and explain it. But this occurs between a lone pair of electrons on an oxygen, nitrogen, or fluorine atom. Sulfur is also an option. I'm going to leave sulfur off, so just for us, oxygen, nitrogen, or fluorine. And a hydrogen that is bonded to an oxygen, nitrogen, or fluorine atom on a neighboring molecule. So it occurs between a lone pair of electrons on an oxygen, nitrogen, or fluorine. So you have to have an oxygen, nitrogen, or fluorine atom. If you don't, you can't have these. And then oxygen, nitrogen, or fluorine has to have at least one lone pair. If it doesn't, you're not going to have these. And then the other molecule, remember these are between molecules, so The other molecule is going to have a hydrogen bonded to an oxygen, nitrogen, or fluorine. So essentially you have to have an OH, an NH, or an FH bond. And then that oxygen, nitrogen, or fluorine has to have at least one lone pair of electrons on it. Water is going to be my example again because water fits this bill, right? Water, I have oxygen. If we were to draw the Lewis structure, I have two lone pairs on that oxygen atom. Let me put another water molecule in here, and it has its two lone pairs. So I'm actually going to put, let's actually just circle one of them. Remember, these are in orbitals. Right, I just want to, I'm going to make it a little bit smaller, but remember the orbital that they're in is just as big as the orbital that's overlapping with the s orbital of hydrogen. I just kind of want to circle it to make my point because I want to differentiate between my dipole-dipole forces. So I have a lone pair on oxygen in my bottom molecule. I have a hydrogen bonded to oxygen in my upper one, and then those are attracted to each other. So it's very similar, but a very fine difference, right? If I go back up and look at dipole-dipole, it's between the partial negative oxygen atom itself and the hydrogen. This is between the lone pair of electrons on oxygen and the hydrogen. If you're not careful, right, it looks like the line's going between both atoms, but one specifically to the lone pair. So for hydrogen bonds, right, occurs between a lone pair on an oxygen, nitrogen, or fluorine, and then a hydrogen that's bonded to an oxygen, nitrogen, or fluorine, versus the oppositely charged ends, right? Or partial charges. They're not full charges, right, because they're molecules, not ions. Our third one are London dispersion forces, which actually has several different names. This is the one that I use. I'm going to use LDF as my abbreviation. But sometimes they're just called dispersion forces. Sometimes they're just called London forces. Sometimes they're actually called induced dipole forces versus dipole. It'd be induced dipole. They all mean the same thing. You can use any of those versions if you want. This is the one that I'm going to use. So this results from a weak, temporary, spontaneous dipole due to the unsymmetrical distribution of electrons. I know that's a mouthful. So it's weak, right? A weak. It's temporary, so we're actually constantly making them and breaking them. I'll explain it more in a minute. Spontaneous, it just happens. We don't have to force it to occur. So we have these weak temporary dipoles that happen. And they happen because of the unsymmetrical distribution of electrons. And that's actually in an electron cloud. So if you have electrons, it doesn't have to be a compound. It could just be an atom, so something like argon. Argon would have these. So if you have electrons, you can have London dispersion forces. So this is the only one that our non-polar molecules are going to have. To have hydrogen bonds is going to be polar. You're not going to have that lone pair on an oxygen, nitrogen, or fluorine and a hydrogen bonded to oxygen, nitrogen, or fluorine, but it's not polar. It has to be polar to have dipole-dipole forces. So this is the only one that non-polar molecules are going to experience. So if the atom or compound has electrons, it experiences this force. I won't give you something that doesn't have electrons. So what that means is if I give you a list of compounds and I say what type of intermolecular forces does it have, always write down London dispersion forces and you'll always get partial credit. You won't have one where London dispersion forces are not an option. So both polar and nonpolar molecules experience this force. So this is going to be kind of a lame picture, but I'm going to draw an atom. So I have a nucleus in the middle, and then totally not to scale, right? If that was the chart, the size of my nucleus, then the first, energy level is way off screen, right? It's not even close. Remember that nucleus is super, super, super small in terms of volume compared to the entire volume of my atom, right? Really, really dense. But I'm going to have some electrons in that electron cloud. And then I have a neighboring atom, because this is between particles. We're just going to use atoms. And it has some electrons. And they're moving around in its electron cloud. And remember, they're following a wave-like pattern. We're using quantum mechanics. They're acting independently of each other, but they're moving around following a wave-like pattern. And they're moving constantly, right? We're not at absolute zero, so those electrons are constantly moving. So at any given time, what can happen is I can take these electrons, so I'm just going to erase this one here and I'm going to move it over. They can be bunched up, so it's not symmetrical anymore, right? They're bunched up on one side. And what do like charges do to each other? Yeah, like charges repel, right? So when this electron, right, they're bunched up on this side, it gets close to this electron because the two atoms approach each other. What happens to that electron in my second atom? Yeah, it's going to repel it. So this electron then moves over here. So now what I have is I have this half of this atom is kind of negative because the electrons are bunched up on that side, right? This side is kind of positive. These electrons are bunched up on that side, so that side's kind of negative, which means this kind of side is kind of positive. So what I have is a temporary dipole, and those guys are attracted to each other. It's temporary because, well, we can't freeze time, right? Those electrons are constantly moving. They're not going to stay bunched up. So what's going to happen then is this electron is going to move back over, this electron is going to move back over, and we're going to break that connection. So we're constantly forming and breaking those. If you have electrons, they can be bunched up on one side of the atom, repelling, right, an electron on a neighboring atom to move. So we're inducing it, right? The one atom is inducing a dipole. So constantly forming and breaking those. They tend to be weak, but if you have a lot of electrons, they can actually sum to be pretty significant. So atoms or molecules with more electrons, right, things that are larger, have stronger London dispersion forces. So if I was to compare bromine versus chlorine, we know from 130 or from high school that at room temperature, right, bromine is a liquid. And we know at room temperature, chlorine is a gas. Right? These are both nonpolar. The only type of intermolecular force that they have are London dispersion forces. So at 25 degrees Celsius, bromine, I still have London dispersion forces, right? They're still being held to each other. That's why it's a liquid. Remember, when we go to a gas, we break those connections. At 25 degrees Celsius, we've already supplied enough energy to break the connections in chlorine. And that's because bromine's larger, right? Bromine is bigger than chlorine. So it has more London dispersion forces, right? More electrons, more of those temporary dipoles. So still a liquid at 25 degrees Celsius. Right, if I wanted to add iodine to the list, iodine is actually solid at room temperature, right? It's even bigger. So I have even more of those connections. So larger molecules, molecules with more atoms or with more electrons, have stronger London dispersion forces. So the bigger it is, the more London dispersion forces it's going to have. We could say larger. The other trend we have are things that have the same size but different shapes. So molecules with the same number of electrons but different shapes, right? Different molecular geometries. The more surface area it has, the stronger the London dispersion forces. Right, to experience those, the two atoms have to approach each other, right? So the one molecule has to get close to the other molecule to induce the neighboring atoms, or electrons, sorry, to move, right? I have to be able to repel each other. The more surface area you have, the more contact you have, right? The more places where you can spontaneously induce dipoles. So the more surface area it has, the stronger the London dispersion forces. We could say the shape is more spread out. And I could use, for an example, let's do C5H12. So I can draw this a couple different ways. I could draw all 5 carbons in a row. Remember, hydrogen can never be in the middle. So if all you have is carbon and hydrogen, I know that the carbons have to be bonded to each other, and then the hydrogens are bonded to it. Carbon wants to form 4 bonds, so if you go and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, that's where the hydrogens would go. I'm going to leave the hydrogens off because I think the picture will be easier to see, so I just want to, I didn't mean to erase all those carbons. I just want to erase the hydrogens. So you can draw it again, all 5 in a row. So that's something that would be pretty spread out, right? What I could do, and there's a couple other ways, but I could put a carbon in the middle if I wanted, and then I could bond that carbon to 4 other carbons. That is not so spread out. And if I was to go and put the hydrogens on it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So they have the same number of hydrogen, right? They're both C5H12. They just have different shapes. So this one, more spread out. Right? What that means is we have more surface area. So stronger London dispersion forces again. And again, because it just has carbon and hydrogen, these are nonpolar, right? Remember, carbon-hydrogen bonds were on our list of bonds that were considered nonpolar. There is an electronegativity difference, but it's so small that we consider that bond nonpolar. Again, if you need to go back and review bond polarity, please do that. One other type of intermolecular force, and we're not going to see that a lot, this applies mainly for solutions, but it's an ion dipole force. I am going to include it because our text includes it. But we would see this one mostly in chapter 11, which is on solutions. So this is between something that's an ion. Remember, ion is a charged atom, so either a positively charged atom or a negatively charged atom. And then something that has a dipole, so a polar molecule. So this occurs, that just got really messy, occurs, that's not much better, between a positively charged ion and the partial negative of a neighboring molecule. Or and, I guess, a negatively charged ion and a partial positive end of a neighboring molecule. These ones are usually pretty easy to recognize because you actually need 2 things, right? I need something that's ionic and I need a polar molecule. So I can't just give you water because that's just a polar molecule. I have to give you something that's ionic and something that's polar. So an example for this one, I could give you an aqueous solution. It can be kind of tricky if I do that, right? Of sodium chloride. So if I have an aqueous solution of sodium chloride, what that means is I have sodium chloride in water. So I have both a polar molecule and I have an ionic compound. Right? So I know sodium chloride is Na plus and Cl minus, right? It's dissociated in aqueous solution, which is what I have. We've drawn water a couple times already in this video. Oxygen's partial negative, hydrogens are partial positive. So if I was to draw some water and then put my partial charges on there, partial negatives, my partial positives, this connection between the positively charged sodium and the partial negative oxygen would be an ion dipole force. I can then draw, if I want another one, let's draw another water over here. This time I'm going to orient it differently because I want the partial positive hydrogen to be attracted to that negatively charged chlorine. So that dotted line would represent an ion dipole force also. We could draw more of them in there if we really wanted. I don't know if you guys really want, I want to. So partial negative oxygen, partial positive hydrogen, and so on. So ion dipole forces. So let's go through some examples. So what types or type of intermolecular forces do the following experience? So we'll do a couple. Let's do CF4. NH3. Krypton. I'm just making stuff up here. And H2S. So the first thing we really need to do is determine if they're polar or non-polar, right? You could just write down and for sure do this. If you can't determine if they're polar or non-polar, remember all of them are going to have London dispersion forces. I won't give you something that doesn't have electrons like hydrogen with a positive charge. Just write down London dispersion forces because you'll get some credit for it. We're not going to do that though. We're going to do the whole thing. So I'm going to draw these out. If you need to go back and review Lewis structures, please make sure you do that because you need to be able to draw these on your own on tests and quizzes. So when I draw this out, I end up that HF4 is tetrahedral. I'm going to assign bond dipoles, and fluorine is more electronegative than carbon is. So I have bond dipoles going in all four of these directions. So one up, one down at 109.5 degree bond angles, one coming out and one going back. So those guys are going to cancel each other out, and this molecule is going to be non-polar. So what type of intermolecular forces does it have if it's non-polar? Yeah, just London dispersion forces, and that's it, right? To be polar, or to have dipole-dipole forces, I have to be polar. To have hydrogen bonds, I have to have that OH, NH, FH bond with a lone pair on oxygen, nitrogen, or fluorine. I don't have that. And then to have an ion and an ion dipole force, I need to have something that's ionic also, and I don't. So just London dispersion forces. So NH3 ammonia, same sort of idea. I'm going to draw that out. I do have a lone pair on nitrogen, and then my 3 bonds to hydrogen. So this one is trigonal pyramidal. My nitrogen is more electronegative. More electronegative than those hydrogens are. So I have 3 of them all going up. So this one turns out to be polar. So what type of intermolecular forces does it have? So London dispersion forces, I hope everyone gets that one, right? We're always going to write it down. It has electrons, they're moving. So London dispersion forces, it's polar. If it's polar, always write down dipole-dipole. And then does it have hydrogen bonds? That's our other one. Well, I do have a lone pair of electrons on nitrogen. I do have a hydrogen bonded to nitrogen, so it meets our criteria. So this one also has hydrogen bonds, so it's going to have all three of them. Krypton is just an atom, there's nothing to draw out, right? If it's just an atom, I don't have any bonds, so it's going to be nonpolar. So if it's nonpolar, just London dispersion forces. And then our last one, H2S. This one turns out to be bent in shape. I do have two lone pairs. So this would be that basic tetrahedral structure. It's just two of those positions are lone pairs and two of them are bonds. So does this molecule turn out to be polar or non? Yeah, polar, good. So London dispersion forces, because we're always going to write that down. Dipole, because it's polar, and every time it's polar, we're always going to write down dipole. And then does it have hydrogen bonds? I have a hydrogen, and I have lone pairs, but it's not an oxygen, nitrogen, or fluorine, so no. Just dipole, and London dispersion forces for this one. So determine if it's polar or not, right? And then based on that, does it have dipole forces? So kind of let's make like a little London dispersion forces, both polar and nonpolar, dipole, polar, and then hydrogen bonds, right? We have to have that OH, NH, FH bond, and a lone electron pair on the oxygen, nitrogen, or fluorine. Be careful, you need both parts, right? Just because I have a nitrogen with a bond to a hydrogen doesn't mean it's going to have hydrogen bonds if I don't have that lone pair, right? If I was to draw ammonium ions, NH4, and there's a formal positive charge on nitrogen, this is nonpolar. It also, so just London dispersion forces, it's also, right, it has an NH bond, but there's no lone pair on nitrogen, so this is it, just London dispersion forces, so be careful. In general, as I go down this list, they tend to become stronger. So they tend to be stronger. There is some overlap. If you have a lot of electrons, right, if your molecule is really big and you have a lot of London dispersion forces, they can actually sum to be stronger than just one dipole force. We won't do that in here. We're going to stick with this list, but do know that there is overlap here. This trend isn't really always this way. If you go on and take biochem, a lot of times we're going to have London dispersion forces that are just going to be stronger because biomolecules are just so much bigger. So in general, this is going to be stronger as we go down.